In this module, you will learn about the fundamental principle of counting. We have 3 balls of different colors and 3 holders. These balls can be placed in the holders in many different ways. First, we will place the yellow ball in the first holder, the green one in the next, and the blue ball in the last holder. We can interchange the green and blue balls and get another arrangement as shown. Similarly, starting with the green ball, we get 2 arrangements as shown. In the same manner, we get arrangements starting with the blue ball too. In total, there are 6 possible ways of arranging these balls. These are the maximum number of ways in which we can place the 3 balls in the holders. What we are interested in here is the number of unique ways in which the balls can be arranged rather than the arrangement of the balls. We will extend this concept of counting further. Let's consider a situation where we are at the town hall in our city. We want to go to the stadium. For this, we have to board the metro train that takes us to the stadium. There are 4 ways that go from the town hall to the metro station, and 3 to go from the metro station to the stadium. We are interested in the number of ways in which we can reach the stadium. We first take route M1 to the metro station and route S1 to the stadium. So our route is M1, S1. We can also take the other possible routes to the stadium as shown. These are the maximum available routes from the town hall to the stadium. Here each route is unique. Together, we have 12 routes that will take us from the town hall to the stadium. As discussed before, we are interested in counting the possible number of routes. An ideal way to visualize the number of ways is using a tree diagram as shown. Here route M1, S1 is as shown. Similarly, the other branches follow. The counting for this situation can be done easily by using the principle known as the fundamental principle of counting, or the multiplication principle. The principle states that if an event can occur in m different ways, following which another event can occur in n different ways, then the total number of the occurrence of the events in the given order is the product of m and n. This principle can be extended for any number of events. Let's use the principle for the situation that we just saw. Let the number of routes possible in the event town hall to metro station be m, and the number of routes possible in the event metro to stadium be s. The number of routes that can be taken from the town hall to the stadium is equal to the product of m and s. Here m is equal to 4 and s is equal to 3. Therefore, the number of ways is equal to 12. In this module, you will learn about permutations. In counting problems, we are often concerned with the number of unique arrangements with the available constraints. Let's see how we can count the number of possible arrangements. Here, take a frame and 3 small square tiles that can be put in the frame. Our study is, in how many ways can we arrange the tiles in the frame? Let's start with a blue tile. We then arrange the other tiles in 2 ways as shown. The other arrangements, starting with the green and yellow tiles, are as shown. We have a total of 6 arrangements. Therefore, there can be a maximum of 6 possible unique arrangements using the 3 tiles. Here, each arrangement is called a permutation. We can define a permutation as an arrangement in a definite order of a number of distinct objects taken some or all at a time. Let's analyze the pattern of permutations. For the first place of the tiles, we have a choice of 3 tiles. When the second position has to be filled, we have a choice of 2 tiles. Likewise, for the last tile, we had only 1 tile. On generalizing, we have 3 tiles for the first position, 2 for the second, and only 1 tile for the last position. Thus, we have the total number of permutations as 3 into 2 into 1. This can be generalized for any number of tiles. For n number of distinct tiles, the number of permutations is as shown. Now, we will see a theorem on permutations. Suppose we have 4 tiles to be filled in 3 places as shown. Here, repetition is not allowed. We have 4 different objects, which are 4 tiles of different colors. This implies n equals 4. To fill up the first place in the frame, we have to take 1 tile from the 4 tiles. This implies that the first place can be filled in 4p1 ways. Now, we are left with 3 tiles. To fill up the second place, we have to take 1 tile from the 3 tiles. This can be done in 3p1 ways. Similarly, the third place can be filled in 2p1 ways. By the principle of multiplication, the total number of permutations is 24. Now, we will see a theorem on permutations. The theorem states that the number of permutations of n different objects taken r at a time, where 0 is less than r is less than or equal to n, and the objects do not repeat, is n multiplied by n minus 1 multiplied by n minus 2 and so on to n minus r plus 1, which is denoted by npr. Suppose there are n objects and r spaces. These spaces need to be filled with n objects. The first place can be filled using n objects in n ways. After filling the first place, the number of objects left is n minus 1. Now, the second place can be filled with n minus 1 objects in n minus 1 ways. Similarly, the third place can be filled in n minus 2 ways. Continuing the same process, the rth place can be filled in n minus r plus 1 ways. According to the fundamental principle of multiplication, the total number of permutations is as shown. This expression is denoted by npr. Here, n is a natural number. To clarify this further, let's take up again the example of tiles that we saw earlier. Suppose if we have 4 tiles to be filled in 3 places as shown. Here, repetition is not allowed. We have 4 different objects, which are 4 tiles of different colors. This implies n equals 4. There are 3 places in the frame. This implies that we take 3 tiles at a time to fill the frame. Therefore, r is equal to 3. Therefore, the number of arrangements can be done in 4p3 ways. This result is similar to the one we saw earlier. Till now, we have come across situations where we multiplied natural numbers as shown here. We will use a convenient representation to depict such products. The representation is called a factorial. For example, the multiplication of the numbers that we saw is represented as shown and is read as 3 factorial. As a general representation, if n is a natural number, then n factorial is written as shown. For n is equal to 4, we have this representation. Now, we will see an alternate representation of NPR. We know the formula for NPR. We divide and multiply by n minus r factorial. Then, we expand the n minus r factorial in the numerator. Therefore, the numerator becomes n factorial. This representation is used for computing NPR. You have learned about permutations. In this module, you will learn about various permutations with given conditions. First, let's see about permutations when repetition of the objects is allowed. The number of permutations of n distinct objects taken r at a time, where repetition of the objects is allowed, is equal to n power r. Suppose there are n distinct objects and r spaces. The first place can be filled using n objects in np1, that is, n ways. Since repetition of objects is allowed, we have n objects available to fill the second place. Therefore, the second place can be filled with n objects in np1, that is, n ways. Similarly, the rth place can also be filled in n ways. By the multiplication principle, the total number of permutations is equal to n multiplied by n, r times, which is equal to n power r. As an example, let's take 4 digits, 1, 2, 3, and 4. The number of 3-digit numbers that can be formed with these 4 digits, when the digits are allowed to be repeated, can be calculated as shown. Here, n is equal to the number of digits, which is 4. R is the number of places in the 3-digit number, which is equal to 3. This implies that the number of permutations possible with the 4 digits, taken 3 digits at a time, is equal to 4 power 3, or 64. Now, we will discuss about permutations when not all of the objects are distinct. Let's use a tiling example. We have a frame and 3 tiles, 1 blue and 2 yellow. We will see how many arrangements we can make with these tiles. For the sake of convenience, we mark the tiles B, Y1 and Y2. Now, the permutations available are as shown. There are 6 permutations. Now, if you remove the marks on the tiles, you will observe that 2 of the 6 possible arrangements coincide with each other. You will also observe that there are 3 similar-looking pairs. In the permutation, each arrangement repeats twice. Therefore, the number of permutations is equal to 3 factorial divided by 2 factorial. Here, 3 factorial relates to the total number of arrangements, while 2 factorial relates to the permutations within similar tiles. This is evident from the figures. Let's consider another example. Let us find the permutations of different words that can be formed with the letters of the word IIT. Let's mark the 2 I's as I1 and I2. The possible permutations are as shown. If we ignore the subscripts, the arrangements look like 3 words. Observe that every similar pairs of words are formed with 2 different permutations of the 2 I's in the word. Therefore, the number of permutations is equal to 3 factorial divided by 2 factorial. We can generalize this in the following manner. The number of permutations of n objects, where p objects are of the same kind and the rest are all different, is equal to n factorial divided by p factorial. In this example, the number of objects is equal to 3. The number of objects being repeated is 2. So far, we have seen permutations where only one type of an object is repeated. Let's now take a look at permutations where more than one objects are repeated. In the word banana, there are 6 letters. The letter A repeats thrice, while the letter N repeats twice. The number of permutations possible with the word banana is 6 factorial. Since the letter A repeats thrice, 6 of the possible permutations or 3 factorial permutations resemble each other. One such set of permutations is shown here. Therefore, there are 6 factorial divided by 3 factorial permutations. Coming to the letter N, we have 2 permutations or 2 factorial permutations that resemble each other. Therefore, we have the number of permutations as shown. This can be generalized into a formula. The number of permutations of n objects, where p1 objects are of one kind, p2 are of the second kind, pk are of the kth kind, and the rest, if any, are of a different kind, is n factorial divided by the product of p1 factorial, p2 factorial, and so on up to pk factorial. Using the theorem, we will find the number of possible permutations with the letters of the word trigonometry. In the word trigonometry, the letters T, R, and O each repeats twice. We will denote them with PT, PR, and PO respectively. The total number of letters is equal to 12. This implies n is equal to 12. Therefore, the number of permutations of the letters of the word trigonometry is as shown. Substituting the values, we get the number of permutations as 5 crore 98 lakh 75,200. The specific case of the theorem is some objects in a given set of objects are of the same kind. In this module, you will learn to select objects from a given set of objects. We have seen permutations of objects. The notion of permutation is based on the order of the arrangement of objects. If we are not concerned about the order of the arrangement, then we arrive at the concept of combinations. To understand this, let's consider 3 points on a plane. Suppose we need to find the number of straight lines that can be drawn through these 3 points. Taking 2 points at a time, we can draw 3 straight lines, AB, BC, and CA. Though a straight line can be drawn from B to A, it is considered equivalent to the straight line from A to B. It implies that AB and BA are equal. Here, we can observe that the order in which the points are chosen to draw a line is not important. A similar analogy can be drawn for the lines drawn from C to B and from A to C. We get 3 straight lines joining points A, B, and C. We can say that the straight lines are drawn taking a combination of 2 points at a time. Now, we will try to establish a formula to compute the number of combinations of any given number of items taken some at a time. Let's take 3 objects, X, Y, and Z. Let us form combinations of 2 objects using the given objects. We get the combinations shown. The total number of combinations is 3. This implies that out of 3 different objects, taken 2 at a time, we get 3 distinct combinations. This can be expressed mathematically as 3C2. Let's write the possible permutations using these objects taken 2 at a time. The number of permutations is 6. If we observe the combinations and permutations, we can see that each combination has 2 permutations. We can see that each combination of 2 letters can be permutated in 2 ways or 2 factorial ways. Therefore, by the multiplication rule, each combination multiplied by 2 factorial ways is equal to the permutation. To verify this, let's substitute the values of 3C2 and 3P2 in the relation. We can generalize the relation for any number of objects. The number of combinations of n objects taken r at a time multiplied by r factorial is equal to the number of permutations of n objects taken r at a time. Let's divide both the sides of the relation by r factorial. Substituting the formula of NPR, we get NCR as shown. Please remember that the value of 0 factorial is always taken as 1. Let's use this formula to compute the number of selections possible for a volleyball team of 6 members that have to be selected out of 8 members. We have to select 6 players from a team of 8 players. Here, n is equal to 8 and r is equal to 6. Therefore, 8C6 is equal to 28. This implies that the team can be selected in 28 different ways. We have seen the permutations and combinations of n objects taken r at a time. In this module, we will discuss some theorems and results on combinations. The first theorem states the relation between the permutations and combinations of the n objects taken r at a time. Suppose there are n objects and we have r places to be filled by taking r objects at a time. The number of permutations is NPR. Here, we can see that the process is of 2 events. The first event is selecting r objects from the given n objects. The second event is arranging these r objects in r places. The first event of selecting r objects can be achieved in NCR ways. The second event of arranging r items in r places can be done in r factorial ways. Using the multiplication rule, the whole process is equal to NCR multiplied by r factorial. Therefore, NPR is equivalent to NCR multiplied by r factorial. Based upon the theorem, we can obtain a few results. The formula for NCR can be written as shown. To arrive at this formula, we use the relation that we just saw. We will divide both the sides of the relation by r factorial. By substituting the formula for NPR, we get the formula for NCR. Using this formula, we can prove that NC0 is equal to 1. This can be easily verified by substituting the values. Another result that we can verify using the formula is NC n minus r is equal to NCR. Let's verify the result by using the formula on the left-hand side. We can see that this is NCR indeed. Another result we can verify using the formula is NCN is equal to 1. Using the previous result, 3, we have NCN is equal to NCN minus N. This implies NCN is equal to 1. One of the important results is if NCA is equal to NCB, then A is equal to B or N is equal to A plus B. Given NCA is equal to NCB. Obviously, this relation holds true when A is equal to B. Next, we will consider the case where A is not equal to B. Without loss of generality, let's take A is lesser than B. We use the formula for combinations on both the sides. The factorials can be expanded as shown on both the sides. The first term on the left-hand side is expanded using the fact that A is less than B. The second term on the right-hand side is also expanded in a similar way. Since either side is the product of B minus A consecutive positive integers, we have N minus A is equal to B. Simplifying, we get the result.